Okay, so 7.1, the second part of this section. We have all of the ones we've derived so far in part 1. So the Laplace of a constant is 1 over s. The Laplace of t is 1 over s squared. And again, this is supposed to be 0 factorial, 1 factorial, 2 factorial. It does fit the pattern. The exponential. And we also have an existence theorem. If the function is piecewise continuous on an interval 0 to infinity, since that's the one we're doing our Laplace on, and the function's bounded pretty much, then the Laplace of f of t exists. So basically it's similar to integrals. Think about the area. If you're integrating, it's the area. If we can find the area, you can find the Laplace. So for piecewise functions, that's what I'm thinking about. So my next example is going to be using a piecewise function. We will be doing a lot more on piecewise functions in other sections. They actually have a name. So we want to find the Laplace of this function. We can graph it if we like for visual. At a, to the left of a, t is less than a. We'll open that and come this way. We'll give it a highlight. Going this way. And let's call that 1. It's filled in. Goes this way. Different color. So there's the graph of it. So since it's piecewise, we have to just change our limits of integration. So the definition, just by definition, it's our function times e to the minus st dt from 0 to infinity. Graphing it for me helps me set up and change my limits of integration. So we can see we definitely want to go from 0 to a f of t. Okay, so let's plug in what we have or what we know. So from 0 to a, t is less than a, the function's 0. So the whole thing just zeroes out. And that will be 0. Kind of turns the function off. When you have a piecewise like that and it's 0, it turns the function off at that interval. And then a to infinity. T is greater than a. It's the function's 1. So we plug in infinity. Well, we'll pull out our constant. I like to do that first. You plug in infinity, and that's 0. You plug in a, and you're plugging it in for t. That's what we get. Do the math. It's 1 over s positive. We can write that as, since it's a negative exponent below, and you can see it's 1 over c's. So our next property has a name. It's called an S translation. And it says, I'm going to box this and I'm going to prove it here in a second. Now, do realize if this were plus k, then this will be the opposite. That'll be a minus. Okay? So here's our proof. Our proof is we're going to work out both sides. and show that they're equal. So let's work out e to the kt. Plugging that into the Laplace transform, it's 0. That's my function. You combine those. And I'm going to do one more step. And you'll see why in a minute. I'm going to pull out a negative there. So that's minus s minus k. You might see where we're trying to go, so maybe you can see why. So that is equal to that. Now let's work out f of... Before we do that, let's find f of s. F of s is little f of t. We don't need parentheses there. So that's just the definition of Laplace of little f of t, yeah? So what I would need, though, if that's f of s, again, let's go ahead and translate that k. So f of s minus k, that means just everywhere I see an s, I transpose it. And you can see this is identical to that, so this is identical to that. They're all equal. So let's do an example. Let's find this, the Laplace. So remember that translation is you have a function sitting next to an e to the kt, and then what you do is you find capital F, the Laplace transform, and then you shift it, k, whatever's in that power. Well, the first two are just review from the last video. E to the 2t is 1 over s minus 2. Cosine is s squared plus 3 squared, and it's s on top. If it were sine, it would be 3 on top. And here we go. We have to, this is my f of t. And so the intermediate, we might want to label that. So f of s. Okay. But we want f of s minus k. 2t. So k is equal to 2. So we replace s with s minus 2. And we get, I just copy the rest. Last example. We just did this up there. We're going to do a piecewise. So 0 to infinity of my function. So we're doing this exactly the same. 0 to a to 0. I'm sorry, 0 to a to infinity. And that first piece is 0. When that first piece is 0, that first integral zeroes out. So let me write it in general. So as I mentioned, 0, that will 0 it out. And this f of t is cosine. So you'll see why I want this in a minute, but we know integrating that's not so easy. So what I want to do is I want this to be 0 at the bottom. So if I want my bottom integration to be 0, I want to do a u sub. And I want, so that's t. We're going to try u. Oh, my a, by the way, is 2. It's right there. It's not in general. It's 2. So if I put a plus 2 and I plug in, no, I want to u sub. That's not going to work. Let u equaling to t minus 2. When I plug in 2 there, I will get 0 there. So du equals dt. Again, it changes lower bound to 0. You can see when I take the t equals 2, 2 minus 2 is 0. I'll get what I want, and we'll still go to infinity at the top. So this is equal to 0 to infinity cosine. We are going to have to substitute for t. T equals u plus 2. And change that to du. They're equal. So what we're going to do here is we're going to break that up. We're going to break it up using the formula, the sum formula for cosine. Remember, it starts there. So the sum formula so remember, it's du. I'm going to break this up. It'll be e to the minus su times e to the minus 2s. S is a constant, so we can bring out the constant in the front, which is e to the minus 2s. And then these are constant twos also. Let me bring that sign of 12 in the front. So now we can see this is a new Laplace. That's our new variable. This is the Laplace of cosine of 6u, which will switch back to our correct variable. And this is the sine. So this, and then the Laplace of that, we don't have to actually integrate. We can find out Laplace. And same with this sine. And there's our answer. Not much to clean it up, but I'll rewrite it. voila. So I just wanted to point out we didn't actually integrate, and that's why we had to replace this 2 with a 0, because the definition, when we use this definition right here, we were using the definition of Laplace where you have to have 0. The definition of Laplace has 0 there. Up here, when we had a here, we didn't need to change it to 0 because we actually integrated it and we used a instead of 0 because that's what was there. So that's the difference. If you're going to integrate, you don't need the 0 there because we've just plugged in the a. But if you're going to go backwards and use the definition, then you definitely need 0 on the bottom. When we were actually on the previous video, if you wanted to go back, we had something similar with the 0 there when we used the definition, this definition, trying to find the Laplace of cosine. You have to use parts twice to integrate that. And so we thought this was a little bit easier. And that's it for today.